Welcome to Astro 101, the Sun and Its Neighbors. I'm Professor Bart Netterfield. In today's class, Class 18, we are going to be talking about how tides in the Jovian planets produce some of the most remarkable structures in the solar system. Last class, we took a quick tour of the Jovian planets. We looked at Jupiter, Saturn, Uranus, and Neptune. We looked at their structure, their atmospheres, and their internal structures. We looked at their moons, and we introduced ourselves to the incredible ring systems around Saturn. And we learned that not just Saturn, but also Jupiter, Uranus, and Neptune all have rings. We looked at the wide variety of moons around these systems, including some of the most geologically active objects in the whole solar system. It was an exciting and kind of a whirlwind tour, but it left us with a number of significant questions. And we're going to try and come back to those questions and answer them. The first question was, what is going on with Saturn's rings? There's these incredibly beautiful, enormous structures, 260,000 kilometers across, but 10 to 100 meters thick, depending on where in them. What causes them? How do these rings come to be? The second question we were left with was looking at the wide range of geological activity in the Jovian planets, going from Io, this small, relatively small moon, which is the most geologically active object in the entire solar system, going out to Callisto, which is one of the most cratered objects in the entire solar system, all orbiting Jupiter. Why is there this range? Well, let's first try and unpack that second question and remind ourselves why we should even be confused. Now, back when you were looking at the terrestrial planets several lectures ago, you learned that the size of a terrestrial planet impacts its level of remaining geological activity. The reason is, in order for there to be geological activity, you need to have convection in the mantle, where warm mantle rock, which is kind of flexible on long time scales, can rise because it's lighter and hotter, and colder, denser rock can sink, causing these convective cells, which in turn produce geology on the surface. Now, it turns out, if you recollect, that smaller objects like Mercury cool faster than larger objects like the Earth. Consequently, Mercury has cooled to the point where it has no more geological activity. It's just a solid, cooled object. Even though it's close to the sun, you think, well, it'll be warmer. Because it's smaller, it's had a chance to cool to the point where no longer does it have any measurable geological activity, while the Earth, being quite a bit larger, has continued to stay warm, continued to have a liquid outer core, continued to have convection in the mantle, causing geological activity. So on Earth, we get volcanoes, we get earthquakes, and other activity. Mercury, and even smaller than Mercury, the Moon, these are smaller objects. They've had a chance to cool, and no geological activity. Then we come to the Jovian moons. Io, Europa, Ganymede, and Callisto. And we notice that, well, Io, Europa, and Callisto are all smaller than Mercury. In fact, Io was around the same size as the Earth's moon. Yet, these objects continue to be extremely geologically active, where these are completely dead. How do we understand that? How do we understand this in the context where we expect smaller objects to cool faster and become geologically inactive, while larger objects should keep their heat longer and be more geologically active? And in fact, what's going on here? Well, let's unpack this a little more. Io, a moon of Jupiter. This one, the one that is around the same size as the Earth's moon, it is an incredible example of geological activity. You look at the surface of Io and you see it's just covered with volcanoes. Here's one in particular. This is a mountain which is around 5 kilometers tall. In fact, that's the typical size to many of these volcanic mountains all over Io. Many kilometers tall. So there's something going on. No evidence at all of craters. So the surface of Io has been completely recovered long since any craters. And in fact, we can see evidence of active, ongoing volcanic activity. When the New Horizons probe was zipping past Jupiter, it caught this series of images of Io, and it showed the volcano Tristar blowing off this incredible plume, 330 kilometers up into the air. That is into the sky. There's no real air around Io. This is higher than the orbit of many low Earth orbit satellites. 330 kilometers into the air, this incredible volcano. Here we can see some pictures taken by the Galileo space probe of that volcano. We can see active lava here. Here, it was so bright that the camera had to disable itself for fear of burning out the pixels or something. But there was active lava going on here as well. Lava flows on this moon of Io. This small moon, smaller than or around the same size as our moon, yet the most geologically active object in the solar system. Why is it? I thought we learned that smaller objects cool faster and therefore should not be geologically active. Why is that rule not working? Why is Io so geologically active? Second one out from Io is Europa, another moon of Jupiter. The surface is covered with uncratered ice. There's a very small number of craters. There's one there that I can see in this picture. But the rest of the surface is this weird structure. It's like this. It's this fissured, structured ice cracks in the ice, something like that. Beyond these structures, Europa is the smoothest object in the solar system in terms of lack of surface features of all the solid objects. What is going on with Europa? So they've done some measurements. Galileo spent a lot of time looking at Europa, and because Europa is so smooth, because the surface is so young, it's not been around. It's not been around much since cratering stopped on these planets. The cracks on the surface, the magnetic field measurements, all these things add together to suggest that Europa is covered by a huge ocean under the ice. Now, it's not certain. They haven't completely verified the existence of this ocean, but that seems to be the best way to explain all these various clues. That underneath the surface of Europa is this large liquid ocean. That's really fantastic. Now let's just stop and think about that for a second. This is an ocean which contains more water than the Earth. This is one of the largest bodies of water, liquid water, in the solar system, underneath the ice cap of Europa. The magnetic field measurements indicate that it's probably salty. So we have a giant salty ocean on Europa. Now, just as an aside, when somebody says, oh, there's a large salty ocean somewhere, you think, I wonder what kind of animals live in that ocean. Is that what you think? We don't know. We don't know if there's nothing in the ocean. We don't know if there's bacteria living in that ocean. We don't know if there's sort of simple jellyfish living in the ocean. We don't know if there's a civilization of 7-headed snakes living in that ocean. We have no idea, because we don't know, A, if the ocean really exists, B, what the conditions are, and C, what conditions are necessary for life to form. Great mystery. Wouldn't it be exciting to find out? Is there an ocean under Europa? And if there is there life in the ocean? So, really, really cool question. There's a number of groups in the US planning to try and send a probe to Europa to try and explore some of these questions. It could be pretty exciting. Or it could find out, like, nope, A, there's no ocean, and B, no, there's no ocean. But if there is, and there's life in it, incredible discoveries await, maybe. Okay. But the question is, why isn't it frozen over by now? This thing is small. It's way out at Jupiter. Why isn't this ocean completely frozen over by now? If it's small, and the rules we learned, small things cool faster, why hasn't it cooled? In fact, when you look at the Galilean moons, the most active is Io, then Europa, then Ganymede, and finally Callisto. Callisto being the least active, the most cratered surface, the oldest surface. Nothing's happened on the surface of Callisto to speak of since the heavy bombardment early on in the solar system billions of years ago. Ganymede, some has happened, but not a lot. Europa really quite young, and Io changing continuously even to this day. Most active, least active. Why? Why is this the pattern? Why not least active and most active? Why not the smallest, the least active, the largest, the most active? Why this pattern? Let's try and understand. We can. I've already given you the clue. I said it's because of tides. So let's go back and review tides. Okay, so remember the story a long time ago, tides. We have the Earth and we have the Moon. That's the Earth-Moon system. We're going to be looking at the Jovian systems in a minute, but let's start with review of what happens on Earth. We have the Moon, we have the Earth, and we have the force of gravity, applying a force between the Earth and the Moon, equal to this equation. The force equals the mass of the Earth times the mass of the Moon, divided by the radius squared, times this tiny number called g, and that gives us the force pulling from the Earth to the Moon and from the Moon to the Earth. That's if you say that the Earth is one thing and the Moon is one thing. But if instead you say, well, the Earth is actually made of a bunch of places. The place closest to the Moon is closer, and therefore it applies a larger force. The place that's further away applies a weaker force. So a stronger force on this side, a medium force in the middle, and a weaker force on the far side. Okay. So what that does then is it tends to cause the Earth to stretch. It's pulling harder here, medium there, the least there, so the whole thing gets stretched out like a piece of taffy. Now, not very much, because the Moon isn't that big. And it doesn't happen right away. Rock takes time to move. It's kind of viscous. It's like taffy. They don't bend quickly. Nonetheless, we expect the Earth to be kind of bent. Well, okay, it isn't, because the Earth is turning. And consequently, it can't get around to stretching into shape. But if you imagine the Earth was covered with water, it would stretch, but it has viscosity too, so it's kind of delayed by a bit. So what we find is the Earth is kind of this, the oceans and the Earth are stretched. Not by much, maybe by a couple of meters, but it's enough that we can have pretty cool effects. And we have these tides occurring. Also, because of this lag, it's applying a force on the Earth, slowing down the Earth's rotation. So what's happening is the Earth's day is slowing down, slowing down, slowing down. Eventually, it would be locked to the Moon. Now, the Earth is too massive. It's going to take too long for that to happen. So the solar system will end before before the Earth is fully tidal locked. Now, the Earth's period was 14 hours when the Earth was formed. Now it's 24 hours, so it's slowing down. This slowing down converts rotational energy into heat. It's like putting the brakes of a car. So that you're continuously squeezing the Earth and letting it come undone. That is actually slowly heating up the Earth a little bit. So some of the heat in the Earth is caused by this tidal heating. Not a large fraction, because the effect isn't very big, the Moon isn't that big, but there is some. Okay. The Moon has tidal locked because the force of the Earth on the Moon is much larger. So now the Moon is tidal locked. It's one side always faces the Earth. Okay, well, let's go and take this concept, which we reviewed, back to our good friend Io. So here's Io. The tidal forces on Io are much greater than on the Earth because of the Moon. Because Jupiter is far more massive than the Earth or the Moon. So the forces of tides on Io are much, much larger. So if Io were rotating relative to Jupiter, if it were spinning, tidal heating would be enormous, right? If it's spinning and it's trying to squeeze Io, and it's like squeezing it this way and then squeezing it this way and then squeezing it this way, you're sitting there squeezing rock, that is going to give off a lot of heat. So that could make sense. Tidal heating, if Io were spinning, tidal heating would warm up Io and make it very hot. But it would also stop Io from spinning and would tidal lock it, and in fact, Io is already tidally locked. So that doesn't work. So early on in Io's time, when it was first spinning, perhaps that was what was going on. It was heating up Io from spinning. But it didn't take long before Io's spinning was slowed down by this heating, and Io became tidally locked. But what if instead Io was traveling in an elliptical orbit. Oh, this has got hope. You start out here. You have relatively weak tidal forces. When you're in here, you have strong tidal forces. Strong tidal forces here, you're going to squeeze a lot. Weak tidal forces out here, squeeze not very much. So what you would expect is if Io were in an elliptical orbit, it would come in, get squeezed, come out, get unsqueezed. Get squeezed, get unsqueezed. So I thought, wouldn't it be fun? We've learned Newton's laws, right? Force equals mass times acceleration, or the speed changes depends on the force you apply. And the amount of the force depends on how far two objects are apart and their masses. So we can take those two equations and we should be able to make a simulation of this system. So I did it. Here's what I did. Pulled out my trusty Rust compiler and built a system with I made a moon out of 1,500 squishy balls. And the moon weighs something like the mass of Io. Not exactly, but somewhere in that area. So we have 1,500 squishy balls. They obey Newton's laws. And they also have some viscosity and some force between them when they're touching. When they're not touching, they're just Newton's laws. When they're touching, there's a little bit of viscosity and a little bit of springiness. So kind of like squishy Nerf balls or something that they're made of. 1,500 of them. And I'm going to solve Newton's laws on every one of them as they bump against each other, and as they pull against each other, and as they pull against Jupiter. So what happens to start with is their own gravity holds them together into a ball. So they formed into a roughly spherical ball because it's massive enough that you can't make a big mountain. It forms a sphere because of the force of gravity. And then all of them as a group are being attracted to Jupiter. So here's Jupiter. Here is my little fake Io moon. We started out in orbit around Jupiter, and we'll see what happens. Shall we see what happens? Let's do it. Okay, here we go. Let's come around. Whoa, look at that. It comes around, and as it comes around, it gets close to Jupiter, and it squeezes out into this oblong thing. It comes out here, and it settles back into a sphere. And then it comes back in, and it gets squeezed again, and it comes back out here, and it settles back into a sphere. Oh, this is cool. So what we're saying is that in elliptical orbit, if Io were this fake moon, if it were an elliptical orbit like this, it would get squeezed and unsqueezed, squeezed and unsqueezed, and that would put an enormous amount of heat into Io. I don't know if you noticed something else. This moon is already tidally locked. You see that? It started out not turning at all, but it didn't take long in this elliptical orbit before it's spinning to keep the same side always pointing toward Jupiter, which is, I don't know, pretty cool. So it works. So this is just doing a simulation of what would happen if you made a moon out of 1,500 squishy balls, and to see what would happen. The answer is you get this squeezing and unsqueezing, and you get tidal locking. Well, that's great. So that's the story. All right, so let's summarize. When Io is further from Jupiter, tidal forces are less. When Io is closer to Jupiter, the tidal forces are greater. Consequently, this changing force distorting the moon heats up the moon. It squeezes and unsqueezes. It squeezes and it unsqueezes. And that continuous force acting on the moon, acting on Io, heats up Io, because Io's orbit is in fact elliptical. Io's orbit is barely elliptical, but it is enough to heat it up. So we solved the problem. This is really cool. Why is Io the most geologically active object in the solar system? Because it's in a close elliptical orbit to Jupiter. But there's a problem. The problem is heating up Io takes energy out of the orbit. So the orbit gradually becomes circular. So why is Io's orbit still elliptical? It should be circular by now. The answer to that question is going back to another thing we looked at in previous weeks, and that's the object of orbital resonance. That's when the various things are orbiting at exact multiples of each other. It turns out that Io, Europa, and Ganymede are in a resonance with each other, a 1 to 2 to 4 resonance. That is to say, Io goes around 4 times, when Europa goes around twice, when Ganymede goes around once. This tends to keep all of their orbits slightly elliptical as they continuously pull against each other. Let's take a look and remind ourselves what a resonance is. Here we go. Here we have Jupiter, Io, Europa, and Ganymede. So starting now, Io and Europa, their Io's gone around once, and then Io now has gone around twice, while Europa went around once. Io went twice, Europa once. Okay, so start now. Io and Ganymede. Io once. Io twice. Io 3 times. And finally 4 times, and Ganymede once. So what happens is Io goes around 4 times, Ganymede goes around twice. Io goes around 4 times, Europa goes around twice, and Ganymede goes around once. And if you notice also that Europa, that they're not all in phase, so you never get all 3 at the same side. This turns out to be a stable pattern, but what it does do is it pulls the orbits into being slightly elliptical. So what we find is that Io's orbit and Europa's orbit are slightly elliptical. Ganymede's orbit is barely elliptical. It's almost perfectly circular now, so we don't see very much heating, tidal heating of Ganymede anymore. Europa gets some, and Io gets a lot. So this explains it. Io is the most geologically active because it has an elliptical orbit close to Jupiter, therefore has very extreme tidal heating. So it gets heated up to become the most geologically active object in the solar system. Europa, it's moderate. It's enough to keep the liquid water liquid under its surface, to be a little bit active, but not crazy like Io. Ganymede and Callisto. Callisto's all by itself, the furthest out one. It's a perfectly circular orbit, more or less. There's basically no heating going on. It is completely dead. Ganymede is somewhere in between. So, most active to least active, because of orbital resonances and tidal forces. Very cool. Okay, that's great. Now, I will say also that in my simulation I did, that was a really extreme case. That was a very elliptical orbit. Io's orbit is barely elliptical. You're not seeing that really gross crunching that I saw in the simulation. The distortion of Io wouldn't really be visible in a simulation, so I kind of made Io get as close as I could without other things happening, so you could really see the effect of the tidal heating. But that is the effect, and if a moon did get in that path, it would get that kind of effect going on. But Io is just less extreme, but the same idea. Okay, cool. We understand this geological activity. Now, another thing that we noticed as we went through the solar system, we saw some moons of some of the planets were completely dead. Others were somewhat active, some were very active, and we didn't really have a way of understanding why. In the end, it comes down to whether or not the orbits are elliptical or not, and how close they are to the Jovian planets. The more elliptical and closer ones end up getting tidal heating and can become more geologically active. The ones that are in a more circular orbit and further away end up with very little tidal heating, or none at all, and end up being less active. And so that's a way now of understanding the huge variation in these moons that we saw, at least some of the huge variation in the moons that we saw. It's the nature of their orbits. Okay, so that was mystery number 1 that we wanted to look at. Let's now look at mystery number 2. What's going on with the rings? Why? Where do they come from? Remind ourselves, the rings are very, 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 very complex. Tons and tons and tons of structure. As we zoom in, we see these bands and we see these gaps, and it just seems like it never ends. You keep getting closer and closer, and you see more and more and more and more structure with these fine, fine gaps and these bands. And what is going on? We also notice that they seem to be ubiquitous. All of the Jovian planets have them. Jupiter has rings. Uranus has rings. Neptune has rings. What is causing these rings? Well, you might have already guessed. given the title of the lecture. Again, could it have something to do with tidal forces? Now, just a minute ago, I showed a simulation where I made this moon of, 1,400 balls and sent it into a tight orbit and saw that it was getting really badly distorted. Let's try that again. The same simulation again, but this time, let's let the moon start a little bit slower. Not much at all, maybe 5% slower. So just barely slower. Okay, so we're starting the moon in an elliptical orbit around Jupiter, but we're going to start it a little bit slower. What's that going to do? All right, let's ask ourselves, what is that going to do? If we start the moon a little bit slower, what will happen to its path? All right, 4 suggestions. It will be an elliptical orbit with the perigee, that's the closest point, a little bit closer to Jupiter. So the closest point will be a little bit closer, or it'll be an elliptical orbit, but the closest point will be a little bit further. Or the path won't change, but the orbital period will change. Maybe it'll go up. Or it will get closer to Jupiter. As it gets closer to Jupiter, it'll speed up, and that'll flick it out, and we'll end up in an escape in a hyperbolic orbit. That's the shape of an orbit of an object going faster than the escape velocity. So it comes in, it gets going fast, and then it shoots out. Or E. I'm not sure. I'm just going to guess E. I can't really comment on E, but it's probably not the answer I was looking for. Which one is it? Do you think for a sec? Right, you can pause it. I'm going to keep going. Answer is A. It will be an elliptical orbit with the perigee, the closest point, a little bit closer to Jupiter. So it's coming in, and it doesn't scoot out as far. It comes in a little bit closer, but just a little bit. I only changed the speed by 5%, so it's not much closer, just a little bit closer. The question is, what is that going to do to the system? Well, let's take a look. Let's run it. So again, we're starting with a moon made of 1,500 pieces of kind of squishy ice. It's about the same mass, roughly, as Io. It's going to come in a high elliptical orbit. It's going to get close to Jupiter, and we'll see what happens. Here we go. All right, here it comes. It's scooting around, and oh, it stretched out, and whoa! Hey, that's hilarious. It just ripped the thing up completely apart. And now I have this shredded thing, and what's it doing? It's forming a ring. Oh man. Look at this. Jupiter now has a ring. We made a ring for Jupiter. We sent in an asteroid or a moon too close, and it broke it up, and it turned it into a ring. And as it goes along, what we'll see is this ring will get more and more filled out. This end here will gradually move in, but it will take way longer than we're going to run it for. And eventually you'll have a beautiful circular ring. That's hilarious. Should we look at it again? Here it comes. It's coming around. It's getting more and more tidal forces, and it gets stretched out, but it got stretched out too much. The thing just completely comes apart and ends up in this long tail that just keeps getting stretched out until finally, after, not too long, you end up with a ring. I think that is super cool. Okay? Start out with the object, comes around, tidal forces begin to work on it. The tidal forces are greater. It's got too much speed. It's greater forces than the strength of gravity to hold it together, and it just rips itself apart and becomes a ring. So, that is a reason that Saturn has rings. Possibly, a moon got too close to Saturn and it broke up and formed the rings. That is a possibility. Now, there's another possibility. You see, anything orbiting this close to Jupiter or anything orbiting this close to Saturn couldn't stay together. If you put a moon in there, it can't stay together. It will not grow gravitationally because the force of gravity is not as the force of self-gravity is not as great as the tidal force is ripping it apart. So you can never get a moon this close to Jupiter or a moon this close to Saturn. So it's the other possibility is that the rings formed at the time of formation of the solar system. All the gas there couldn't form moons, it just stayed as a disk. So there's two possibilities. One, something came in and got torn apart and formed the ring, which I just showed in the simulation. Or two, the stuff that was there at the formation of Saturn was just always there, and Saturn's always had a ring. The former explanation is preferred for various reasons, but both are possible. And we don't currently have a good way of distinguishing between them. If we can come up with a way, that would be really cool. In the meantime, we're not really sure, but we do know that tidal forces prevent a moon from forming at the distance of Saturn's rings, a large moon forming at the distance of Saturn's rings, and that if a large moon did get there, it would get shredded and form rings. So there we go. Pretty cool. But that's part of it. Now we know why it has rings. But what's with all these gaps? What causes all the gaps in the rings? Huh. Okay. Let's do an instant quiz before we answer the question. Compared to particles on an outer ring, compared to particles in an inner ring, particles in an outer ring do what? A, orbit faster. So inner ring, do they orbit faster? Do they orbit slower? Do they orbit at the same speed? After all, it's a disk. It depends on the mass of the particle, or you're just going to guess E. Particles in an outer ring do what? Do they orbit faster, slower, same speed? Depends on the mass of the particles. Or E. The further out you are, the slower the orbit is. So outer particles orbit slower than inner particles. That means that if you look at the ring and look at some particles in the rings, these ones will be going slow, these ones will be going fast, these will be going in between. So all these different bands, all these different particles in the bands are all traveling at different speeds. Okay, that's interesting. Now can we think of some reasons why you might have gaps? Remember when we talked about the asteroid belt, that Jupiter caused gaps in the asteroid belt because of resonances? The same thing can happen here. So here's an example. Here's the moon Mimas. Here's what's called, it's actually not the moon Mimas. You couldn't really see it in this picture, it's too small. That's actually a white dot in the editor, so you can actually see it. But okay, Mimas would be there. Here's what's called the Huygens gap. The small moon Mimas creates the Huygens gap via a 2-to-1 resonance. Particles here would go around twice when Mimas goes around once. Except for particles right at the right distance. This gap, particles orbiting in there, it's unstable, and they're going to get kicked out of that orbit. And so, you get a gap. Mimas keeps pulling on any particles in here, keeping them from staying in that gap. So, Mimas creates this gap through 2-to-1 resonances. There's other gaps, other structures in the rings, which you can show are resonances of various known moons. So, known moons can create these gaps. All right, so we got another thing going on. Let's imagine that we've got, here's the moon Pan. Pan is orbiting at this distance. Particles inward of Pan are going faster, so they try and pass, and when they do, they get deflected. Particles outward of Pan get passed by Pan, and Pan deflects them. And so Pan deflects anybody orbiting near it. So Pan creates this gap just by orbiting in the middle of the gap. Now, as far as I can tell, every time you see a new object in the solar system, you have to say, what is that? And this is one of the most what is that's I've seen for a very long time. 3 years ago, in 2017, getting toward the end of its mission, the Cassini space probe took these pictures of Pan. Here we have Pan. It's a disk. It's got cracks. We've seen that kind of stuff before, but what is this? It's got a frill, like a space jellyfish. This frill turns out to be right in the plane of the disk. What's causing the frill? That's so cool. Is it strong? Is it weak? We don't know. What we know is these pictures of it. The universe is so cool. Every time you turn your eyes, you see some new, amazing, majestic thing that God came up with to say, ha, figure that out. And you're like, ah, it's so cool. And then you try and figure it out, and it's really cool. All right, Pan, what are you? Why are you there? And what is this frill? Anyway, in the process, though, we did figure out what caused this gap. So some of the gaps are caused by orbital resonances. Some of the gaps are caused by small moons orbiting in the disk. What else we got? We have these disks here, and here we have a video of the moon Prometheus coming by, and Prometheus is sitting here disturbing this ring, pushing particles in. As it passes, it pushes the particles into the ring. It's acting as what's called a Sheppard moon. So it pushes the particles inwards and keeps the ring narrow. See? Well, that's cool. Out here, this moon apparently doesn't do much at all to the ring. It's too far out. But this one comes quite close and leaves a wake behind it, which keeps the F ring kind of narrow. Acts as a Sheppard moon. Okay, so there's another thing that can happen. Another way you can get structures in the moon is structures in the rings is having moons orbiting in the gaps and again distorting the ring and pushing it out and keeping it fairly narrow. So Sheppard moons. That's thing number 3. Again, it seems to be because of moons and the force of gravity acting on the rings, making gaps and making structures. Okay. Here's another thing. This is really cool. Here's a small 8 kilometers across, small room Daphnis. It caused this gap, and you see it causing these weird waves. And these waves are sticking up above the disk, and so you can see it casting these shadows. And these are, a couple kilometers tall. The disk itself here is something like 10 meters thick. It's very thin. Very thin. It's like the thickness of my house. Yet, it's making these waves that are going up a couple of kilometers high. And here's Daphnis going by and doing it. That's really cool. So we have another example of a moon causing a gap, but also causing these funny waves. Neat. We have other examples. These are very small, tiny moons, 100 meters across, traveling in the disks, making these tiny little gaps and these really cool little wakes around them as they travel. So it seems that a lot of the structure in the rings is caused by gravitational interactions with small moons. Small moons orbiting outside the rings or inside the rings, causing this structure. And here we have another example. These weird waves, 2.5 kilometers tall, out at the edge of the B ring. We don't know what's causing all these waves. Probably there's some small moons embedded at the edge of the ring causing them, but that's a likely thought. We haven't actually identified those objects. Lastly, here's another cool thing going on. Here is a picture of a section of the rings, but with a UV camera, so an IR camera, infrared camera, so we can look at how long wavelength light is being scattered from the structures. And in this IR false color image, blue means either the particles are larger, or it means that there's more water ice in them. So blue bands here, that means more water ice, or maybe the particles are just larger. Red means there's less water ice, or it means the particles are smaller. And you see a lot of structure in this. what we're saying then is that the composition of the material in the rings varies as you go across the ring. So that's another thing that's changing. So you have gravitational interactions. You have two things going on then, right? You've got gravitational interactions with the moons causing gaps, and you have varying particle properties causing changes in the structure, therefore changes in the way that the rings look. So two things going on: gravitational interactions with other moons and varying particle properties. So there we've done it. We've gone through, and this is a nice short lecture compared to the really long one last time. We've gone through and we've researched two very interesting questions. One, what causes all this crazy volcanic activity and geological activity in some of the Jovian moons, and why are some of the smaller moons so geologically active? The answer is elliptical orbits near Jovian planets cause tidal heating, and being in a resonance with another moon can keep that elliptical orbit going. Second thing is, where do the rings come from, and what's all their structure in them? The answer, the rings come from, again, tidal forces either stripping apart a moon that got too close, or not allowing it to form in the first place. Then gravitational interactions with very small objects, not so large that tidal forces tear them apart, can tend to mildly distort the rings and cause these beautiful gaps and structure. So this has been a really quick, but I think really interesting lecture on a couple of really cool things. This is my second to last lecture for the semester. Next class is going to be really cool. We are going to take a tour and a survey of the wide range of amazing probes that have gone out to explore the solar system. Everything from flyby missions like New Horizons that shot past Pluto and took those amazing pictures, to landers such as the ones that have gone to Venus or to Mars. Robots like the one now that was driving around recently on the moon. So it's going to be a fun lecture as we just learn about how do we explore the solar system. I'm looking forward to it, and I'll talk to you then. Thanks.